Hi everybody, welcome back. Today I'll be looking at functions of a random variable as I continue the probability primer. Let's get into that. The lesson overview for now is, well, what did we do last time? I looked at tons of moments and moment generating functions, and I hope we had a lot of fun there. In this lesson, let's suppose I know everything about a random variable, not only the moments, just everything. What can I say about functions of the random variable? In particular, what's the distribution going to be looking like? And this has absolutely huge implications in this course, especially in random variate generation. Here's the problem in general. Let's suppose I have a random variable x and I completely know the probability mass function or the probability density function. In either case, it's f of x. And let's look at the function of x, h of x, I'll call that y. We saw h of x notation when I used lotus in the last lesson. Let's let this arbitrary function of x be denoted by y. And what I want now is I want g of y, the PMF or PDF of y. So I've got the PMF or PDF of x. Now, what's the PMF or PDF of that function of x? So it's very important. Here's some examples, and take my word on this that these work. It turns out if x is normal, 0, 1, we'll talk about that distribution later on. It so happens that if I take the square of that, I get a chi-square distribution. Even if you don't know what those are, if I square normal, I get a chi-square. It's because of this lecture. Now let's look at a uniform distribution. Let's suppose I start with a nice, easy uniform 0, 1 distribution. We've actually seen this. If I take the function negative 1 over lambda of natural log of that uniform, I get an exponential. Amazing. So I start with the uniform, I plug the uniform into this little equation here, negative 1 over lambda natural log of u, and I miraculously get an exponential lambda distribution. This has huge implications in random variate generation. So let's start off with a very easy discrete example. I'm going to let x denote the number of heads from 2 coin tosses. And I'm going to derive the PMF for this function of x, y equals x cubed minus x. So anyway, let's look at the PMF of x first. X is the PMF of, from 2 coin tosses, so it can equal 0, 1, or 2, with corresponding probabilities a quarter, a half, and a quarter. So let's look at the corresponding values for y. If x equals 0, then y equals x cubed minus x equals 0. If x equals 1, then y also equals 0. And if x equals 2, then y equals x cubed minus x equals 6. So you can see the values of x equals 0 and 1 map into y equals 0, and the value of x equals 0 maps into y equals 6. So what does this imply? Let's add up the probabilities. The probability that y equals 0 is the probability that x equals 0 or 1. Add those up. A quarter plus a half equals 3/4. The only other possibility for y is y equals 6. And the probability of that is 1/4. I didn't have to do much thinking there. That corresponds to x equals 2. So, in other words, the probability that y equals 0 is 3/4. The probability that y equals 6 is 1/4. That is my PMF of y. Very, very easy. Let's do a continuous example. This one's a little bit more challenging. Now suppose x has PDF, because it's continuous, f of x equals absolute value of x. And this is going to be defined for x between negative 1 and 1. It looks like this, sort of a reverse triangle. It goes from -1 to 1. And you can see that if you take the integral of this thing, you can almost see in your head that it integrates to 1. It's a legitimate PDF. Given that as my starting point, let's find the PDF of the function y equals x squared. Okay, well, here's what you do. Here's how you find these things. I'm going to find the CDF first, CDF of y, then I'll take the derivative. So this is the usual way you do these problems. You find the CDF first, then you take the derivative. Here's the CDF. Now, I want to do as little thinking as possible because I'm totally lazy. So let's just kind of do things by the book here. The CDF of y is a capital G of y, and that is, by definition, the probability that y is less than or equal to y. That's just by definition. No thought whatsoever. Okay, again, in my quest not to do any thinking, let's just plug in. What is y? It's x squared. So that's the probability that x squared is less than or equal to y. And now, let's remember that I only know stuff about x. I know everything there is to know about x. I don't know this x squared stuff. So how do I transform x squared to x? Well, you take the square root. So that's what this next step is. The probability that x squared is less than or equal to y is the probability that x is between negative square root of y and plus square root of y. We had to be a little careful when we take the square root to remember that minus part. Okay, well, what is this now? By definition, it's the integral of f of x dx from negative square root of y to plus square root of y. And f of x is square root of x. After a little algebra, you get that result equals y. And so I can get the PDF of y now by taking the derivative. Derivative of the CDF is the PDF. And even I can take the derivative of capital G of y equals y. That's just little g of y equals 1. And what that means then is that y is uniform 0, 1, because that is the PDF of a uniform. So if you start out with f of x equals absolute value of x from negative 1 to 1, and I square it, unbelievably, I get a uniform distribution. And maybe I'll give you a homework assignment on that sometime. You'll see for yourself that it works. Even if you use simulation, you'll get a nice uniform distribution. So this phenomenon is related to what's called the inverse transform theorem. This is a fantastic theorem that's used all the time in simulation. You'll see why in a little while. Let's suppose that x is a continuous random variable, and the CDF is denoted capital F of x as usual. Unbelievably and amazingly and stupendously, capital F of capital X, so this thing is a nasty random variable. Capital F of little x is a CDF. That's just a function of real numbers. But capital F of capital X is a nasty random variable. But we don't have any problems with that. It's just some random variable. If I plug capital X into its own CDF, amazingly, I get a uniform distribution. That's what this theorem says. Here's the proof. And I'll just do this very quickly. We're going to see the proof again. So don't worry about it if these steps scare you. We'll let capital Y equal capital F of capital X. It's just a nasty function of x. Then the CDF of y is, let's do as little thought as possible, probability that y is less than or equal to y. That is by definition. Now I'm lazy. I don't know nothing about y. So let's plug in what y equals, capital F of capital X. That's all that we've done here. Now, I only know about x. So what I'm going to do is I'll take the inverse of both sides. So in this step right here, I take capital F inverse of capital F on both sides. The F inverse of both sides gives me the next step, probability that x is less than or equal to F inverse of y. Where did the capital F go? Well, when I did the inverse of F times F, I got cancellation. And so that's why I'm left with the plain old x then. All right, well, this is going to happen a second time. Let's do the probability that x is less than or equal to F inverse of y. By definition, that's capital F of F inverse of y. The F and the F inverse cancel again, and I get y. If I take the derivative, just like before, I get the uniform distribution. So that's the proof. Very, very, very nice. And we're going to encounter this a couple other times very soon. It's just tremendously important to generating random variables during a simulation. Let's do a simple example now to show how to generate random variables, in particular the exponential distribution. And I'm going to use the inverse transform theorem to do this. So let's start out real easy. Let's suppose that x is exponential, and we know from a previous lesson that the CDF is capital F of little x. That equals 1 minus e to the minus lambda x for x greater than or equal to 0. So now I'm going to use the inverse transform theorem. I plug in capital X into its own CDF, capital F of capital X equals 1 minus e to the minus lambda capital X. The inverse transform theorem says that that thing, messy as it may be, is uniform. Thank you, inverse transform theorem. Since it's uniform, well, let's set it equal to u. And supposing I can generate a uniform from Excel or someplace. So set capital F of x equal to u and solve for x. So that's, I'm going to take the inverse sort of. I'm going to solve for x. After a little bit of algebra, and we'll step through this later on, step by step. After a little bit of algebra, x equals negative 1 over lambda natural log of 1 minus u. And so, since x started out as exponential, that means that negative 1 over lambda natural log of 1 minus u is itself exponential. So if you can give me a uniform, I can give you an exponential. It's brilliant. So for instance, if lambda equals 2 and u equals 0.27, I plug in lambda equals 2, u equals 0.27 right there. And I get x equals 0.157. That's my exponential 2 random variate or realization, they call it. Here's another example. This is the Weibull distribution. I'm going to just walk you through this very quickly. Suppose X has the Weibull distribution. Turns out that mess is the CDF. 1 minus e to the minus lambda x, all that raised to the beta power. The Weibull distribution is a complicated distribution used in reliability theory, and you can see that if I set beta equals 1, the exponential is actually a special case. So if I set capital F of x equal to u, just like before, and solve for x, you can show, do this during the commercials tonight, that x equals 1 over lambda minus natural log 1 minus u, all that raised to the 1 over beta power. You can do that yourself. That's like a little exercise for you. And what I'd like you to do, if you have a little extra time, I'll make this an assignment at some point. Pick your favorite values of lambda and beta and generate a bunch of x's. You can then make a histogram and you got yourself a Weibull distribution. One nice thing is to look at different values of lambda and beta and see what the thing looks like. It turns out that if beta is less than 1 or beta greater than 1, the thing looks very interesting in comparison. I'm going to do a quick bonus here. I'm going to walk us through this very, very quickly because it's already been a tough lesson. But if you are really, really stout of heart, let's look at this bonus result. And I'm not really going to hold you responsible, but I'd like you to see it. In fact, if you don't want to look at it, go ahead, go to the summary. But if you got a couple minutes, take a look. This is just another way to get the PDF of y equals h of x for some very nice continuous function h. This looks a little like Lotus, and we'll be talking about Lotus on the next page. So here's another way to get the PDF of capital Y equals h of x for continuous function. It avoids getting a step or two. It looks a little more complicated, but it turns out it's kind of more direct. I'll just step you through this very quickly. The CDF of y is, by definition, probability that y is less than or equal to y. I'm lazy, so I plug in y equals h of x, and then I take the inverse of both sides. If y is nice and continuous, I can take the inverse, and that gives me the probability that x is less than or equal to h inverse of y. By the chain rule, and since the PDF has to be greater than 0, I take the derivative of this thing right there. Little f of y is the PDF of y. I take the derivative of the CDF. And now I use the chain rule. X equals h inverse of y. Here's the derivative from the chain rule. Looking awful, but that's what it is. The fact that the PDF is positive means that I take the absolute value of that term. So I'll use this result to prove Lotus. So here's the expected value of y. Remember, y equals h of x. That's what Lotus is, expected value of y. This equals, by definition, so I haven't evoked Lotus, I'm going to prove it here. By definition, this is the integral over the real line of y times the PDF of y. That's the step right here. I plug in, using the chain rule expression from the previous page, that awful mess from the last page. That's what that mess is. And now, if you're willing to believe that the absolute value mess times d of y is merely expressed as d of h inverse of y, and it kind of makes sense because the dy's cancel in the previous line. And then I set x equal to h inverse of y. You get this result, which is in fact Lotus. Absolutely amazing. Here's a summary of what we just did. This is a long, difficult lesson, but we got through it just fine. We looked at distributions of functions of random variables. And perhaps the most important thing for this class is that along the way, we use the inverse transform theorem to turn uniforms magically into arbitrary distributions. We looked at the exponential and Weibull. You give me a uniform, I'll give you any distribution you want. And this is extremely useful in simulation all the time. So next time, if you like one random variable, you're going to love two. We'll generalize a lot of the results that we've done over the last couple lessons into bivariate distributions, random variables with two components. So looking forward to that, and we'll see you next time.